Here's my chart, which I like even better because I show a whole bunch of p-values and the corresponding unit circles in this LP distance thing. Few things to note. Notice that 2 is the only possible value for p that is invariant to rotation. If you take your data and you rotate it, the distance does not change. And that's a property people seem to like. With these other values, that's not so much the case, but there's an interesting thing people have noticed. As the dimensionality tends to get larger, the value for p that yields the optimal result tends to get smaller. Isn't that kind of interesting? Yeah, as the dimensionality of your data gets bigger, so if you started if your original problem was, figuring out who's happy in your database of customers and you know their name and address and phone number, probably P2 or something big is going to work well. If you start going into documents where you've got 60,000 words and you're measuring very high dimensional data, it tends to get closer to p equals 1 or even smaller that yields the best values. I don't know if that came out very clear. The notion here is that as dimensionality increases, there tends to be 1 or 2 dimensions that are really, really important. Whereas when the dimensionality is small, there tends to be more of this invariant distance type concept. Yeah?
Does this depend on whether the data is positive or not?
You know, I don't know what it depends on. I didn't do this study myself. I read a paper that said it, and I'm kind of repeating from memory, and it's been a while, so I don't want to fix too much meaning on this for you, but it is a pretty well-established trend that you want your P to be a little bit smaller for high-dimensional spaces. And there tends to be more of an axis-aligned thing going on in data sets that have very, very high dimensionality. By which I mean, you see how the unit circles, put that in air quotes here, because they're not circles at all, obviously, are more and more axis-aligned the smaller P seems to get. That kind of suggests that if you've got a few values that are spot on, that says a lot in high-dimensional space. Whereas in low-dimensional space, you kind of want all the values to be the same. And not sure really why that is, but if you ever do some experimentation, there's a lead to look into. Okay. So there's LP norm. In my experience, I never use LP norm because while it's kind of a cool idea, I find that it doesn't offer a whole lot of value. I usually either want to work in crazy high dimensional space, in which case one of those sparse metrics is usually going to be the best. Or I want invariance to rotation, in which case Euclidean distance is the best. So I personally think LP norm has no real value except as an academic curiosity. But there's a lot of people that use it for various purposes, so yeah, I don't want to take a stand on that. Yeah, okay, I'm going to totally back down on that statement. There are people that use this, and I'm sure they have good reasons. How about that? Okay. Talked about that. Oh, one last thing we need to talk about is the triangle inequality. Has anybody heard of the triangle inequality? Did I close my browser? Okay, triangle inequality. The triangle inequality says the sum of the lengths of any two sides of the triangle is greater than the length of the third side. Okay, example. A, B, and C. The length of A is greater, no, the length of A is less than the length of C plus the length of B. The length of C is greater than the length, or is less than the length of A plus the length of B. The length of B is greater than, less than the length of A plus the length of C. And that will happen no matter how you make the triangle, right? You can try to make the wonkiest triangle imaginable. If we use Euclidean distance, the triangle inequality always holds. Because any side of this triangle will always be shorter than the sum of the lengths of the other two sides, right?
What if you take instead of using Euclidean flat space, you change it to like surface of a sphere?
Yeah, then I believe so surface of a sphere, unless you start crossing the hemisphere point, you can still claim that it's true. But when you start wrapping around the sphere, it stops being true. I'm a little uncertain about that. So here's where that comes in play here. Remember, actually let's just go back to this picture here. In our assignment, we're doing this. Wait, something doesn't look right. I'm in AI. Cyan is the color of this class. Okay. Remember, we're calculating this distance to the KD node. I'm going to copy this, paste it here, so I can draw on it. Do you see that we're assuming that the distance to this node conservatively underestimates, use green so we can see it better, conservatively underestimates the distance to some point inside of that KD node, right? And we're assuming that because there's some distance from that point we measured to that node, and then we're ultimately going to say, hey, that must be greater than the distance to that actual point itself. And therefore, because it is, we can feel comfortable knowing we're not going to miss any point inside of this KD node. In other words, the KD tree concept is going to continue to work with any distance metric you provide as long as that distance metric is compatible with this property of the triangle inequality. So the question is Pearson's correlation coefficient compatible with the triangle inequality? It was cosine similarity. And I could make you memorize that, but the easiest thing to do is cosine similarity. I haven't actually checked. I hope it's there. Let's find out. Triangle inequality. It is important to note, however, that this is not a proper distance metric as it does not have the triangle inequality property. Therefore, do not try to use cosine similarity with a KD tree. You might get imperfect results. Now, having said that, it might give you good results anyway, but you don't have a guarantee of finding the k nearest neighbors. Okay, Pearson correlation. Let's find out if this is a proper distance metric. Triangle. Oh, come on. Somebody needs to update the Wikipedia page to specify whether or not Pearson's correlation coefficient follows the triangle inequality. Triangle inequality. Let's see if Google knows. Hey, somebody's going to make charts for us. And there's a bunch of words. And I'm sure the answer is in there. But hey, have you ever wanted to go update Wikipedia? Now here's your chance. Go find this fact and add it to the Pearson's page. It should be there. So we're going to end this lecture on I don't know the answer to that question, but I hope that Pearson's follows the triangle inequality. Maybe that's why people use it instead of cosine similarity. I don't know. Okay. I think I'm done with KNN. Anything else that could be said about k-nearest neighbors algorithms? Great.
Quick question.
Yes, please.
What is the recent research that has been done to KNN? What is pretty well established theoretically?
It is pretty well established. There's so my advisor did a whole bunch of work on KNN. Let me see if I can find that. Martinez and Wilson KNN. Should probably do this on Google Scholar. So there's studies on k-nearest neighbors as imputation metrics. Here, let's actually do see what's going on with KNN lately. So they used it in some health study, support vector machines mixed with KNN. Machine learning KNN, a lazy learning approach to multi-label learning. Yeah, since 2017. Okay, here's stuff that's been happening really, really recently. So people are using it in specific studies. Feature selection for KNN classifier. So obviously with KNN, if you can reduce the dimensionality, you're going to save yourself some time. There's speed things, there's ensemble approaches to mixing different distance metrics. There's a lot of, I don't know, there are still some open questions. I'm going to say though, as a whole, KNN is a pretty well-established learning algorithm. I don't think that this is ever going to be, I don't think KNN is coming back. I think it's here to stay because it's a simple algorithm and it's well understood. The concepts in KNN, though, come up a lot, and so I do think it's a valuable thing to know. Here's a thought I was having lately. Since I only have about 4 minutes, let me just share a research thought and see if anybody's interested in this. So my idea was this. It's obviously pretty important to tune the weightings of the features in KNN, right? Because basically, if you could, it's really great to use Mahalanobis distance where you scale the deviation out of the attributes, and that way they all carry equal value. But if you could get them all to carry the value that's really, how much they really carry towards the labels, then you'd get a much better KNN, right? The problem with KNN is it's really hard to tune those, and it seems to me the reason they're really hard to tune is because you have discontinuities in the state space. Darn it, I closed that book. Let's see if that can open again. Remember those pictures I was showing you about how the state space is somewhat discontinuous? I was hoping I'd just recognize them. There we go, right here. So for example, even if you use a large value for k, there's still these hard lines that occur in the model space. So when you make predictions with KNN, there are always places where if you take a tiny step from right here to right there, your classification changes drastically. And that always occurs with KNN. No matter how large your k is, until your k approaches the number of data points in your data set. Well, if we contrast how that affects the optimization of the various attributes, of the weightings of the attributes, it occurs to me, I bet you get stuck in local optima when you butt up against these walls. Does that make sense? Because there's got to be some point where there's a single data point that's affecting your accuracy and you don't want to cross that line. Whereas, if we really wanted to optimize our feature weightings, what we'd really want is a space that's nice and continuous, because then we could expect that at least a linear model is going to not get stuck in local optima and is going to converge towards the optimal feature weightings. So it seems to me that the idea of using NNN, where n is the number of data points, right? That didn't come out very well. If you make k go all the way up to n, so you're using all of the data points and you're using some kind of Gaussian kernel for the distance, then you get a nice continuous space. The only problem is it's crazy expensive to compute the nearest neighbors. Well, however, in that space, you're not going to get stuck in local optima while optimizing the feature weightings, and that's a very useful thing to do. So I could imagine somebody writing an algorithm that maybe samples your data and then optimizes the feature weightings and then goes back to the original data and applies full KNN. Maybe that would add a lot of value to it. So hey, there's some research that could be done if anybody's interested in that. Let me show you another bit of research that I thought was kind of fun. Somebody was into pruning and they awarded somebody a PhD for this algorithm. And by they, I mean some academic institution. So imagine you have a bunch of data points and you want to classify them. What they did is he performs KNN. Let's see. Got to remember how this algorithm actually works. You perform KNN on all the sample points, and then you find all the cases where the data points are entirely homogeneous. So there's no conflict going on over here, right? And there's no conflict going on over here. But right here, if you find the k nearest neighbors, hey, they're heterogeneous. Well, if they're homogeneous, then doesn't that suggest that you don't really need these points because the ones right next to it are going to carry the same value to you? So he was able to prune the values way down to the point where as long as the nearest neighbors all have the same value, you can kind of get rid of the points. And in the end, you end up with the minimal set of points that are necessary to achieve the same model space, approximately. And so this ends up making KNN a lot more efficient because you can make your data set much smaller. And there, someone got a PhD for that. Yeah.
How does this make it any different from using SVM with the slack variable?
How does it different than using an SVM?
SVM with slack variable.
That's a good question. So yes, there are similarities there. Differences are that we're still using a distance metric rather than a linear separation, and we're not using the kernel trick here. Yeah, I guess I don't want to say they're all that different. There's a lot of similarities there, and I think that's kind of the stronger point. A lot of these algorithms start to be the same once you really understand them, and I think that's a good observation. Anyway, I'm over time, so I better let you go. Thanks for coming.